So looking at applications to second order linear differential equations, in particular those with constant coefficients, let's consider the LRC series. Okay, LRC series circuit. So here we have an inductor, and inductors have inductance L, okay? So that's the inductance measured in henries is the SI unit. A resistor with resistance R measured in ohms. A capacitor with capacitance C measured in farad. And a source of voltage in the series circuit, okay? It's a time varying function. We just represent it here, E of t. Now the voltage across an inductor is given as the inductance of the inductor times the derivative of the current with respect to time, which is the second derivative of charge with respect to time. Why? Because current is the change in charge over the change in time, dq dt. The voltage across the capacitor is the charge in the capacitor over the capacitance, and the voltage across the resistor is the resistance times the current, or the resistance times dq dt, because the current is dq dt. Now Kirchhoff's second law tells us that the potential difference across any loop in a circuit is equal to 0. So if we go across this circuit, we get a potential difference E of t from the source minus VL minus VR and minus VC, and then that's one loop, and so we get this equation here. And plugging in the relations for potential across these elements of the circuit into our equation, we get this right here, and then moving the negative terms to one side, we get this, okay? Where L is seen as a parameter that's a constant, R likewise, and C likewise. So what do we have here? We have a second order differential equation in charge with constant coefficients, okay? It's non-homogeneous when the source is non-zero. Now, this looks awfully familiar because we've just been, we spent a lot of time talking about it. This is very similar to the spring mass system with driven motion, right? All you have to do is identify the mass with the inductance, beta with the resistance, and the spring constant K with 1 over the capacitance. So there's that 1 over that you should be wary of. And F of t, the force of the driving force with the potential across the source, okay? So no need to reinvent the wheel here. We're not gonna go through and do everything that we've done for spring mass system. We're basically gonna take that spring mass system template and make these super basic identifications. Something to note here is that from this differential equation, you get these roots, okay, of this auxiliary equation. And we're left with the three cases that we've had for our previous spring mass systems, okay? In particular, when what's in the square root is positive, we have an overdamped system. When it's equal to 0, we get one repeated root, and we have a critically damped system. And when this is negative, we get two complex conjugate roots, and we get an underdamped system. And again, the discussion just carries over. Let's take a look at a quick example. Find the charge on the capacitor in the LRC series circuit. So find the charge here. You want the charge function, okay? You want the solution to that differential equation. The inductance is 0.25 Henry, resistance 10 ohms, capacitance 0.001 farad. And here we're dealing with free or undriven electrical potential of the source. So the source is not applying a potential difference on the circuit. So it's undriven and free. Q of 0 is equal to just, we're going to treat this as if it's a constant, this parameter Q naught and I, we have 0 current. Well, taking this differential equation and just plugging in the numbers that we have here, we get this differential equation, which could be rewritten this way. Looking at the auxiliary equation, we get these two roots, and we get this general solution. Now we fix the constants by looking at the initial condition. Q of 0 is equal to Q naught. This gives us C1 is equal to Q naught. The current is the derivative, so what we would do here is take the derivative. I don't write it just because, you know, you get the product rule and some terms. But you would take the derivative, plug in 0, and set that equal to 0, and you get that C2 is equal to Q naught over 3. And so we get this solution for the charge. Okay, you can see that it eventually goes down to 0 due to this exponential term, so you get oscillations, and then it eventually goes down to 0. This is an underdamped system, which could also be written if we combine the cosine and sine as this, okay? All right, let's look at one more example. So find the steady state solution and the steady state current on an LRC series circuit when the impressed voltage, so now we have driven, a driven circuit. The source has a non-zero potential, okay, and it's sinusoidal. It varies as gamma t. So we want the steady state solution, and we've seen before how the complementary solution goes to 0 here. It's a transient term. And so we're just going to focus on QP, the particular solution, okay? That's going to give us the steady state solution. That's the steady state solution is the solution where the transient terms die out. And in this situation, that happens to be QC, okay? So we're going to ignore the complementary function and just focus on QP. We're going to use the method of undetermined coefficients. We're going to assume this form. We're going to plug in QP into the differential equation here. You get a bunch of terms. Set that equal to E naught sine gamma t. So you'll have the term in front of the sine gamma t. That should be equal to E naught. Okay? And you'll have another term in front of the cosine t that should be, you know, whatever term you find when you plug this in, set that equal to 0, and you get these two solutions for A and B. Something to note, XL, the inductance times gamma, the frequency, the angular frequency that the external source is being driven at, is called the inductive reactance, and XC, 1 over C gamma, is called the capacitive reactance. And the reactance is equal to the inductive reactance minus the capacitive reactance. Okay, that's the reactance, and we just call it X, rather than X sub L or X sub C. The impedance is the square root of X squared plus R squared. Now we could square both of those terms, okay, and the reason we square them is because, well, you know, now we could identify the squared terms with what's going on in the denominators there and also in the numerators. So we get here that in a much more compact form, we get A is equal to this and B is equal to that. And so here goes our steady state solution. How do we get the current? Well, we just take the derivative of our steady state solution for charge, and we get the steady state current. So that's that problem. And I'll just quickly mention here that if you take an introductory physics course, you will solve the series LRC circuit that we have here. But in physics textbooks, they do it quite differently. They don't typically solve the differential equation, okay? But here we actually solved it How physics, introductory physics, of course more advanced physics, it's actually all about the differential equation. But in introductory physics courses, they use phasors, okay? They'll assume that the steady state current has this form. Just make that assumption. And the voltage across the inductor will then, the current is proportional, is the potential difference across the resistance is proportional to I, which is represented by this phasor. And the inductor is 90 degrees ahead, okay? In the capacitor, the voltage across the capacitor lags the voltage across the resistor by 90 degrees. Okay? And then the problem becomes solving for, Emax and phi. You could see here, you could get the relations. I won't go into that here. Physics textbooks go through this extensively. But just to kind of draw parallels with people who might have seen that form of solution and are wondering, how does this relate to that? Okay. Finally, we have what's called a torsion spring, which rather than a spring mass system where you get this force and translational motion, you get a torque and rotational motion. Okay. And it looks like this. We won't get into it, but it also has the same form with constant coefficients, for these parameters, and a driving external torque. And our discussion for the spring mass system could also carry over for this system. So, yes, we've been looking at solutions to differential equations with constant coefficients extensively. Of course, there are many differential equations with variable coefficients, and there are ways to deal with that depending on the class or case that you're looking at. Okay, there's a multitude of different classes for variable coefficients. Nevertheless, although it seemed restrictive to look at differential equations with constant coefficients, we see that there's actually rich models in physics and more generally that respect the general form of these differential equations. And so we're actually armed with a powerful tool for modeling.